Welcome to The Explainer. Today, we are taking a rather dense set of university math notes and transforming them into a clear visual journey through the mechanics and geometry of linear algebra. Look, if you've ever stared at a wall of equations and felt completely overwhelmed, you're in the exact right place. We're going to strip away all that noise and look at what is really happening under the hood.
Here's the roadmap for today. We'll meet the linear system, enter the matrix, master the art of row reduction, look at vectors and the span, compare homogeneous and non-homogeneous systems, and finally, wrap up with linear independence. Let's dive right in.
Part 1. Meet the linear system. Finding intersections. At its core, linear algebra is really just a highly structured way of solving a super relatable problem, finding exactly where different lines intersect in space.
Whenever we're staring down a system of linear equations, and I don't care how massive or intimidating the dataset seems, we basically just have to ask ourselves two fundamental questions. First, existence. Is there at least one solution at all? And second, uniqueness. If a solution does exist, is it the unique, single truth? Keep these two questions in the back of your mind, because they're the compass guiding everything we do today. Geometrically, this is beautifully simple. On the left, we've got parallel lines. They never cross, right? So no solution. The system is inconsistent. But look on the right. Intersecting lines give us exactly one unique point of truth. One single intersection means one unique solution to our system. Moving on to part 2. Enter the matrix, a better filing system. It's easy enough to find the intersection of two simple lines visually, but how do we efficiently solve these systems when they get complicated? We all probably remember that old-school, messy algebraic elimination method from early math classes, right? You subtract equations, find y, plug it back in to find x. It works fine for two variables, sure, even if it completely destroys your eraser in the process. But try scaling that exact same method up to a 3-variable system, solving for a, b, and c. And man, it quickly becomes a tangled web of letters, numbers, and arithmetic. Honestly, it is so incredibly easy to make one tiny sign error here and completely derail the entire puzzle. So clearly, we need a better filing system. And this brings us to the matrix. Think of a matrix as this highly efficient organizational tool. It absolutely strips away all those distracting variables, the x's, y's, and z's, and leaves only the core numbers, the coefficients, that we actually need to solve the problem. It takes the total chaos of algebra and locks it into a clean, rectangular array. Which brings us to part 3, the art of row reduction, simplifying the matrix. Now that we have our data neatly organized, how do we act as the cleanup crew to process it and find our solution? We use 3 remarkably simple moves to systematically simplify things. 1, we can interchange or swap any 2 rows. 2, we can multiply a row by a non-zero number, scaling it up or down. And 3, we can add a scalar multiple of one row to another. What's truly fascinating here is that these 3 elementary operations let us completely reshape the matrix without ever changing the actual underlying solution of the system. If we keep applying these steps, it transforms our messy matrix into row echelon form, or REF. Just look at that highly satisfying descending staircase of leading non-zero numbers. We call those numbers pivots. Notice how everything below and to the left of a pivot becomes a 0. It's starting to look a whole lot cleaner, right? But why stop there? Taking it one step further gives us reduced row echelon form, or RREF. Here, we've used our row operations to turn those staircase pivots into clean ones, and crucially, we zeroed out everything above them too. Once your matrix looks like this, the final solution is incredibly easy to literally just read straight off the right-hand side. It is the ultimate mathematical cleanup job. All right, part 4, vectors and the span, the underlying geometry. Let's zoom out from the mechanical math for a second and look at the actual space we're playing in. Instead of just staring at rows of static numbers, try imagining the columns of our matrix as directional arrows living in physical space. See how we can take the arrows on the left and add them together using the parallelogram rule to find a new destination? And on the right, we can also scale them up and down. When we mix adding and scaling, we're creating what math calls linear combinations. And this leads us to a truly massive concept. When you consider absolutely all the possible linear combinations of a given set of vectors, stretching them, shrinking them, flipping them, adding them together in every conceivable way, you get what we call their span. The span simply represents the entire geometric space that those specific vectors can reach. Part 5. Homogeneous versus non-homogeneous systems. Let's categorize these to understand their deeper geometric structure. The core difference here is surprisingly simple. A homogeneous system is just set equal to 0. Because of that, it's always consistent. It always has at least the trivial 0 solution, meaning if you set all variables to 0, it works, so it passes exactly through the origin point. A non-homogeneous system, on the other hand, is set equal to some vector b. It doesn't automatically pass through the origin, so it requires a bit more investigative work on our part.
But here is where the absolute magic happens. This is basically our visual climax for the day. If a non-homogeneous system actually has a solution, that solution set is the exact same shape and structure as the homogeneous system, just shifted through space. You literally just take the flat line or plane of the homogeneous solution and you slide it over by one specific vector, which we call p. It's just a really beautiful geometric translation.
Finally, Part 6, Understanding Linear Independence. Avoiding redundancy as we wrap up our journey.
Look, efficiency in linear algebra is all about avoiding redundancy. If two vectors fall on the exact same line, like those red and blue arrows grouped together, they are linearly dependent. One is literally just a scaled version of the other. Geometrically, that second vector is redundant. It doesn't help us reach any new space. But on the right, if a vector points in an entirely new direction off that line, they're linearly independent. Together, they open up a whole new dimension, giving us completely new geometric information to work with.
So I want to leave you with a provocative thought. We've just seen how matrices strip away the noise to find core truths, and how linear independence weeds out redundant information. When you're out there analyzing complex problems or massive data sets in the real world, can you use this matrix mindset? Can you spot the redundant dimensions or the linearly dependent variables hiding in your own data? Because I promise you, once you can do that, you're not just doing math anymore. You're seeing the matrix. Thanks for joining me on this explainer, and keep questioning the data.